This video is going to discuss what half-life is, how to calculate problems that involve half-life, and where you could find values for half-life on your reference table. So I know you've already learned what a half-life is in earth science, but let's just go over it one more time. So the half-life is how much time it takes for half of your sample to decay. It's not dependent on factors such as temperature, pressure, and concentration. So we could look up the value of the half-life of any sample that they're going to ask you about on the reagents using reference table N. So if you turn to your reference table and look at table N, you'll see that you have the isotope listed with how much time it takes for the sample to decay, the half-life. So the top has, if you look at the very first example, gold, it has the unit in days. Then you have Y as years, going down, calcium is in milliseconds. So the letter after the half-life tells you the unit of time. So Y is years, D is days, H is hours, S is seconds, and they even have milliseconds listed there. The value is listed on the table because the value will not change if it's a different temperature or pressure. That's what we mean by the value stays constant. The half-life value does not change. All right, so what is half-life showing you? How much time for half the sample to decay. So if we start with one whole sample of something, after one half-life, you have a half. After a second half-life, you have a fourth. After a third half-life, you would have 1/8 of the sample remaining. If we had another half-life, a 16th, and then a 32nd. So it's showing you the amount remaining, basically, in this picture after each half-life has happened. The value will never actually reach 0, though, so the amount will dwindle down but not get so much to be 0. So let's look at an example. If I started with 100 grams of something, and I told you the half-life was 10 minutes, after one half-life you would have 50 grams of the sample, after a second half-life you would have 25 grams of the sample, and after a third half-life 12.5 grams. So 12.5 grams would be remaining at the end of 3 half-lives. Some Regents questions are going to use that wording. What is the fraction remaining, or what is the amount remaining? If I ask you for the amount of grams remaining, I'm looking for the end product here, in this case 12.5. If I asked you what fraction would remain, the fraction would be 1/8. Some questions are going to give you the end value, 12.5 grams, and ask you what was the original amount. So in that case, you would work backwards. So the original amount is always going to be more, since you keep dividing to figure out what the half-life is. So if I said what was the original amount, you would multiply by 2 each time and go backwards to figure out what you had to start with. This graph over here is showing you the amount of half-lives on your x-axis and how much is remaining on your y-axis. So starting with 100 grams, after one half-life you have 50 grams. You could just go over and read your graph. It's just showing you the exponential decay pattern over there. So let's go through some examples. What's the number of years that must pass before 25 grams of an original 100-gram sample of carbon-14 remains unchanged? So what I like to do is I like to write out what I'm starting with and what I'm ending with, and I divide each sample in half. So I started with 100 grams. After one half-life, I'd have half of that, which would be 50 grams. After a second half-life, I would have 25 grams. So if you notice, we had 2 half-lives. Next, what you're going to do is you're going to go look up, well, how much time does it take for half the sample to decay? So the sample I'm looking at is carbon-14. Let's go back to table N and find carbon-14. Come on. Okay, so if we look at table N, we see that the value for carbon-14 is 5,715. Didn't mean to cross that out, sorry. So 5,715 years. So going back to our example, so looking back at the example, what you would do is you take your 5,715 years and you would multiply that value by 2. So we get 11,430 years. All right, let's look at the next example. After 32 days, 5 milligrams of an 80 milligram sample of radioactive isotope remains unchanged. What is the half-life of this element? So they tell us what we start with. We started with 80 milligrams. They tell you what you end with, 5 milligrams. So what I do is I make these arrows. So you're dividing the sample in half. So 80 divided by 2 is 40. 40 divided by 2 is 20. 20 divided by 2 is 10. 10 divided by 2 is 5. So there were 4 half-life periods. So if you take 32 and you divide it by 4, that tells you that the value of the half-life is 8 days. So 8, 16, 24, 32 will add up to the total amount of time. The value of the half-life remains 8 because the half-life value doesn't change. Last example, determine the total time that must elapse until 1/4 of a sample of Rn222 remains unchanged. So if I have 1/4 of a sample remaining, well, how many half-lives would that be? After one half-life, you have 1/2 of the sample remaining. So that must mean that we had 2 half-lives if they say that 1/4 is remaining. So we have 2 half-lives that have gone by, but I don't even know how much Rn222's half-life is. So what I have to do is go to my reference table and find Rn222. So let's do that. Rn222, 3.823 days times 2 because there are 2 half-lives. So 3.823 is the value of one half-life. Since we had 2 half-lives, we're going to multiply it by 2. So the total time that must have gone by is 7.646 days.